In order to build the machine, I am going to use some materials. These two plexiglass discs, 30 cm in diameter and 3 mm thick, will be the main part of the machine. I will glue to them a certain number of metallic sectors, made with this copper foil. The machine works by inducing electric charges on these metallic sectors, while the two discs rotate, respectively, clockwise and counterclockwise. With this wooden plank, I will build the base for the machine, then the two upright supports, and two couples of wooden cylinders that, suitably shaped, will make two perfect pairs of pulleys. I will use these leather straps, bought in a sewing machine shop, as transmission belts to connect the pulleys. One of the straps has to be crossed in such a way that the two discs rotate, as said, clockwise and counterclockwise. The plexiglass cylinders, 5 cm in diameter and 15 cm high, will be used to build a pair of capacitors, obtained by gluing a foil of conductive material inside and outside, like in leather bottles. So, now the main parts have been completed, and we can start building the Wimshust machine. Here there are the wooden structure, already partially assembled, all the pulleys and the relevant straps, already cut at the right length, the two plexiglass discs, completed with 24 metallic sectors each, different metallic parts that will be used to assemble the machine, and two copper rods that will be used as neutralizer bars. As brushes, we will use suitably shaped copper foils, glued to a plastic base to make them flexible. In order to complete the system, we will need to add collectors, capacitors and electrodes. These are the missing parts needed to complete the machine. The capacitors have been obtained by gluing a couple of copper foils, properly resized, inside and outside plexiglass cylinders. In order to cover the two open ends of the cylinders, suitable plugs have been prepared, with hood and cork discs. So, after quite a few days of hard work, the Wimshust machine has been completed by adding the capacitors, the electrodes, and a pair of new collectors. With respect to the original design idea, the shape of the collectors has been modified in order to allow for some slight misalignments in the rotation of the discs and to increase the efficiency of the charge collection process. As you can see, a couple of so-shaped pieces of Domopac, thin aluminum sheet taken from my mother's kitchen, have been added to the collectors. So, now, by putting the discs in rotation, we can see that sparks are generated across the electrodes, which proves the right behavior of the machine. Before moving to the experiments, it's worth spending some words about how the machine works. We will use an animation in which the steady state of a working machine is shown. This status is reached after a few turns of the crank, due to initial small charge imbalances in the sectors, because nothing is perfectly neutral in nature. Let's look at the animation and consider a sector on a rotating disc, let's say A, that has just transferred its electric charges to a collector, and this does neutral, gray. While the discs are spinning, this sector moves across another sector, let's say B, placed on the counter-rotating disc, which is still charged because it has not yet reached the collector. Due to electrostatic induction, electric charges in A dispose themselves in such a way that the upper and lower surfaces of A have, respectively, the same and the opposite sign of B. On the other side of the machine, the same phenomenon happens to another pair of sectors with reversed sign charges. When a neutralizer bar creates a shortcut between two opposite sectors, these ones are charged thanks to the electric charges of opposite signs that flow between them. In the animation, sectors turn from gray to blue and red, while crossing neutralizer bars, and go back to gray when they reach again the collectors. The charging process is very similar to the one that happens in volt electrophorus, when one surface of the metallic plate is connected to the ground. In this way, sectors are progressively charged, and these charges are accumulated in the capacitors through the collectors. When the voltage difference between electrodes exceeds the air dielectric strength, which is about 3 kV per millimeter, a spark is generated. Since we have obtained sparks of about 1.5 cm, the corresponding voltage difference between capacitors was near to 45,000 volts. As first experience, we've built an electroscope, i.e., an instrument capable of detecting the presence of electric charges. This one has been made with a glass container, originally filled with onions, a short piece of copper tube, and a thin stripe of aluminum sheet, bent in two equal parts and attached to the tube, which is the electrode of the device. We originally made and obviously used this device to test the Wimshot machine when we weren't yet able to produce visible sparks, due to excessive charge dispersion into the wooden structure of the machine. As you can see, if we put the instrument near the working machine, the two halves of the aluminum stripe start moving due to the repulsion caused by the charges of the same sign. The second experiment I'll show you is the electrostatic ping-pong. Once you have the machine, the rest of the work is quite simple. In fact, you only have to connect two conductive surfaces to the electrodes of the machine, and then put a metallic pendulum between the two surfaces. As you can see, we've built the two surfaces by attaching two pieces of an aluminum foil to a couple of wooden plates. In order to begin the experiment, you only need to swing the conductive sphere such that the sphere touches one of the plates while cranking the machine. The sphere will become like charged, be repelled, and swing across the gap to the opposite plate. Charge transfer again takes place, and the sphere swings back to the first plate, and so on. The sphere will continue the back and forth oscillation for as long as one provides fresh charge via cranking the Wimshot machine. The third experiment is the electrostatic motor. It requires the same base and wooden plates of the last experiment, but this time the pendulum will be replaced by a plastic bottle acting as the rotating part of the motor. The plastic bottle has been perforated in order to be able to rotate around a fixed axis, which has been made with an aluminum tube. Some aluminum stripes have been glued to the bottle to act as electrodes of the rotating part. The static part of the motor is built by gluing a couple of brushes, made with thin aluminum foil, to a couple of metallic supports taped to the conductive surfaces of the plates. When we connect the two metallic surfaces of the static part of the motor to the Wimshot machine and start cranking it, the bottle starts rotating around its axis. This is due to the electrostatic interaction between the two surfaces and the stripes glued to the bottle, which are charged through the brushes.